Okay, so we want to begin our discussion of differential equations, in particular a system of linear differential equations. We will begin with the case where they are homogeneous, and I want to make a jump from one dimension, or rather one differential equation, to a system. So imagine we had three functions, for instance, ft, g of t, and h of t. And let's suppose that these functions are somehow related, or in particular, their first derivatives are somehow related to one another. And here I'm going to be hypothetical and say, let's suppose that f prime of t is equals to, let's say, a times f itself, f the function, plus, let's say, b times g of t, plus c of h of t. That could be one equation, and the second one would be that the derivative of g gives us, let's say, d of f of t, so d times f of t, d times f of t plus e times g of t plus, let's say, j times h of t. And then finally, let's say the derivative of h of t, this is equal to what? K times f of t plus L of g of t plus m times h of t. The idea is that, again, these functions, they share some kind of a relation. That is, if we take the first derivative of the function f, what we'll obtain is a linear combination of the functions themselves. So these kinds of functions, we call them, they are coupled. These are coupled differential equations because the derivative of f gives us something that depends on f itself and also on g and also on h. The same is true of the first derivative of function g, and the same is true of the function h prime of t. Each time we take a derivative of these functions, we get something that depends on all of them. Of course, here I have taken a rather general situation. It could be that maybe they don't all depend on every function. In other words, h doesn't have to depend on all three. F prime doesn't have to depend on all three. It could just depend on f and h, or just g and h, or just h itself. But the point is, the most general case would be something like this. This is a system of linear differential equations, which is homogeneous. So because of this, we can collect, because these functions or these equations are coupled to one another, we can collect them into a nice container using the idea of matrices. So let's suppose we were to collect the derivatives into something like f prime of t, g prime of t, and h prime of t. So this is some ordered column. This is just an array of these derivatives. And then obviously this will be equal to, and just to save time, I'm going to copy this and then paste it down here. So this is what this array would look like. Oops. So in this array, we would have this. Notice that this array here has 3 rows. So you have row 1, row 2, and row 3. And how many columns does it have? In other words, columns that go down, it only has 1 column. The same is true of this one. Although it's a little spread out, it only has 1, 2, 3 rows. But how many columns does it have? Well, this is a sum of what, this is one term. This is a sum of things. So we're going to get one entry here, and that's a sum of things. That's also one entry, and that's a sum of things also. That's also one entry. So actually, although it doesn't look like it, this also has one entry. My point is, what is on the left side is something that has 3 times 1 dimensions, and this stuff on the right hand side also has 3 times 1 dimensions. Okay, now let's focus on the stuff that's on the right hand side. This can be written as a product of a matrix and a matrix that's multiplied to a column vector. And the way we would obtain that is basically that we could write this as A, B, C, D, E, J, K, L, M. And this would be our matrix, and our column would be f of t, g of t, and this would be h of t. So, therefore, these 3 coupled homogeneous linear differential equations can now be written as a matrix equation which specifically takes this form down here, g prime of t and h prime of t. Suppose we were to call this, maybe let me go one step further. Because everything in this column is a derivative of something, we can pull out, or we can make the differentiation operator explicit. So we could write it as d dt, because that's what our function is in terms of. This is going to be f of t times g of t times h of t. I'm sorry, not times. This is just the different entries. And this would be equal to A, B, C, D, E, J, K, that's K, L, M. And this would be, well, as it was before, it remains as it was, and then h of t. Now, if we were to assign a name to this column here, suppose we were to give it one name, or collective name if you like, we can therefore make this equation look a lot more familiar. Let's suppose we were to give this thing here, this whole column here, we were to give it a name, call it x of t. In order to distinguish it from being a regular function, we want to make sure that people understand that it's not just a regular function, but it's a collection, it's an array of functions. We use the typical vector method of putting a bar. So that's going to be x bar. Well, if this thing here has been called x bar of t, what should this be? Well, they look exactly the same. So this also ought to be x bar of t. But notice what's on the right, it's not just x bar of t, but it's the derivative of x bar of t. So therefore, we must appropriately indicate that with a prime. Suppose also I were to call this block here, this matrix here, give it a name. Let's call it A, uppercase A. Therefore, this equation takes this form that this is uppercase A times x bar of t. This is where this idea of a system of linear equations, a homogeneous one that is, can be, this is where these equations arise from. It's that you are starting off with individual equations, but these equations have functions that are interdependent. This derivative of f somehow is related to g and h, and the derivative of g is also related to f and h. But moreover, the derivative of h is also related to f and g. So this enables us to therefore employ the trickery, if you like, or the methods of linear algebra in order to find solutions to this. So this is just to motivate where these kinds of equations come from and what they mean. Although here we were dealing with a case that is three-dimensional, primarily the reason why I say it's 3 is that these columns have 3 entries. So, and also that means we're going to be looking for 3 functions. And the matrix here is 3 by 3. So the point is this problem is a 3D problem. So this problem lives in R3 or in complex space 3, depending on what kind of solution you're looking for. But the point is it's a 3-dimensional problem. We could have done this. Suppose we had more than 3 equations. Let's suppose we had 5 more equations. Well, we would appropriately extend these columns and also appropriately extend this matrix here and also this column to 5 dimensions. Okay, I hope that that's a bit of a good motivation as to how do we even end up with these equations. They solely come from these kinds of relations, but then we use the methods of linear algebra. In order to employ the methods of linear algebra and matrix manipulation, we use we collect them into matrices and vectors. Then we will resume our discussion further on, we will take this point as our launch pad later on.